All right. Hi everyone, how are you guys doing? Hope you're all fine. So today, yes, I am back with my regular settings. I am back with my iPad. So yes, I remember on Saturday we had this problem that I had some issue while connecting my iPad. So today, don't worry, it will be all fine. All right. All right. So first of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And here in this channel, everything is being taught to you completely in English, so that you're not feeling left behind in case you are uncomfortable with Hindi. All right. So we really hope that this English channel benefits all the students who are not very comfortable with Hindi. All right. And I'm sure for students who are comfortable with Hindi, there is already a lot of content that is available on YouTube. All right, so that was the idea behind this new channel. Hi Nishant, how are you? So for those of you who are joining me for the first time, this is a series that I run daily at 9:15. This is meant for 2020 aspirants. Okay, so here we take up topics one by one, and we are only going through the key concepts, and we're focusing on problem solving. So this is the lecture 5 of fluid mechanics, and today we'll be talking about viscosity and surface tension. All right. So moving forward, let me just introduce myself one more time for those of you who don't know who I am. So my name is Rohit Dixit. I study mechanical engineering from IIT Delhi, and I have 7+ years of teaching experience for. So I've been teaching physics for IIT JEE for almost 8 years now. So all my teaching has been so far in the offline setup. All right. So I've taught at some of the biggest names in the offline coaching industry, and I've been doing that for a long time now. All right, I myself was JEE ranked 447, and I've already coached many students to top ranks in IIT JEE on the offline setup. I really hope that I can continue doing that with you guys here on this online platform. So moving forward, it's worth mentioning the benefits that you can get with your Unacademy subscription. So Unacademy has provided me the opportunity to reach out to students online, and it also gives you an opportunity to keep studying online even in this period of lockdown where you can't go to your offline coachings. So Unacademy is providing you benefits like live classes. You get to interact with your educators. So these 2 points make your online class experience very close to your offline class experience. All right. So as I said, I also was teaching offline before this. This is my first online venture. And obviously, I also had my reservations about online teaching. And I was like, I don't know if it really is that effective as the offline setup, because in offline setup, the students are sitting right in front. All right. And we have a two-way interaction, good two-way interaction. But here, I think Unacademy is making it possible for all the students to get that experience online also. You also have live polls and leaderboards in your classes, so which make the classroom more interactive. Okay. You also have live test series and analysis sessions, and you have live doubt clearing sessions, which is very important. I know a lot of students keep on posting their doubts to me these days, and they are clueless about where to get their doubts cleared from. So in Unacademy, every course has this compulsory feature where after every 3 sessions, the fourth session has to compulsorily be a live doubt clearing session. So with your Unacademy subscriptions and in your Unacademy courses, your doubts are always taken care of. So don't worry, you don't have to worry about that. All right. Next, with this subscription, you're getting access to India's best educators on a single platform. So that's a huge advantage. All right. So how do you get this subscription? Very easy. You install the app. Once you have done that, you go to the plus section, you select your goal as IIT JEE and click on that get subscription button. Now, if you will notice that the fees of these subscriptions have been kept very fair and very reasonable. This is much smaller than fees that people pay for their class 7th and 8th tuitions per month. Okay, and you're getting quality education for IIT JEE exam like IIT JEE at these prices. So I think it's this subscription is definitely worth having. All right, I have been associated with the offline institutes. I know the kind of fees students pay there, and this fees is absolutely nothing compared to whatever fees you might be paying otherwise for your JEE prep. All right, so this affordable education can become even more affordable if you get your subscriptions using my code, which is RD Live. So use this code to get your Unacademy subscription to enroll in my courses, and this will also give you an additional 10% discount. All right, so if you are following us on the JEE English channel, you can also follow us with the help of the link shown above, so that you're not missing out any sessions and lectures which are being held on the JEE English channel. Okay. All right, so let's see who all are here. All right. Okay, yes, I know. So today there's something different that was happening. My laptop froze, but don't worry, I've restarted it and everything looks fine now. All right. Okay, so Kumar Nishan says, sir, do something for 2020 aspirants. Take one shot of class 11th for revision. So for the entire class 11th, obviously, the one shot would have to be at least like 50, 60 hours long. What I'm doing, Kumar Nishant, is that I am taking up one shot sessions on the app. You can follow me. You can find my one shot sessions on the app. I am taking class 11 topics. I am doing what you want me to do. So I've already taken a one shot session for kinematics. I've already taken it for Newton's laws, work, power, energy, and momentum. All right. So you can follow me there. Okay. All right, Kumar Nishant. Okay. Hi to you, Harsh. Okay. There is slight. There is stormy and rainy weather at my end. So yes, that might be causing some problems. Okay. All right. Let's hope it goes smooth now. Okay. So as I said, we were discussing about viscosity. So first we need to talk about Newton's law of viscosity. All right. So what is Newton's law of viscosity? Newton's law of viscosity says that. So first of all, let's talk about viscosity. Okay. So viscosity is an internal friction in a fluid. All right. So viscous forces oppose the motion of one layer of fluid over the other. All right. So that is what viscous force is. When two layers of fluid are trying to move one with respect to another, then the force that opposes this motion is called the viscous force. Okay. Now, this force of viscosity, this is an experimental result. Experimentally, it was found that the force of viscosity is directly proportional to the area of the two layers in contact, and this force is also directly proportional to velocity gradient. So, velocity gradient, what is that? That is the rate at which the velocity is falling from one layer to another. Okay. So you have F is directly proportional to A times dy over dv over dy. And if you introduce a coefficient of a constant, a proportionality constant, then what you get is what is B? Oh, Lakshmi Gautam, I don't know what you're referring to. So if you introduce a proportionality constant, then our equation becomes F equals minus neta A dv over dy, where neta is called the coefficient of viscosity, and you will see a minus sign. Minus sign is meaning that the flow, this force is in the opposite direction of the relative flow. Okay, that is what this minus sign is telling you. All right. So let's move forward and talk about the coefficient of viscosity. So coefficient of viscosity is a constant for a liquid, and it depends on the nature of the liquid. All right. It also depends on the temperature, by the way. Its SI unit is decapoise or Pascal second, and it is usually determined experimentally with the help of Stokes law. Here I would like to add one more point. Let's add one more point quickly. Viscosity, coefficient of viscosity changes with temperature or depends on temperature. So coefficient of viscosity depends on temperature also. Temperature of the liquid. All right. So this is also worth adding here. All right. I hope the stream is going smooth now. So Moisha, if you could let me know quickly if the stream is fine now. Is it better now? Okay. Let me know because I think from my end there is no problem. Technically yes. Technically yes, but we ignore that. We ignore that. That is why it turns out if you're moving faster, it actually also depends on your relative velocity. Okay, but again, as far as your JEE syllabus is concerned, you don't talk about those effects. Okay, all right. So we ignore that. We ignore that dependence. We assume it to be independent of the temperature, by the way. Okay. So don't worry about that. Now let's also talk about Stokes' law and the terminal velocity. So you know that Stokes' law, what is that? So that gives you a relationship of the viscous force that acts on a spherical body. So please remember, it only talks about a spherical body. So only on a spherical object. This is telling you the force due to viscous forces. Alright. So when any object moves through a fluid, it experiences a viscous force which acts in the opposite direction of the velocity. Obviously, in air we call it the drag force. Alright. This viscous force on a spherical object of radius r moving with a velocity v in a uniformly viscous liquid is given by 6 F equals 6 pi eta RV. So this is an instantaneous equation, by the way. Here you are putting the instantaneous value of velocity and instantaneous value of force. You're getting, all right. Only defined for spherical objects. Okay. So now, what happens is that if suppose I have a long tank and if I dropped a small sphere in it, so initially its velocity would be zero, so it will feel a force of gravity because of which it starts accelerating. And as it gains speed, there is a force which starts opposing, and this force is increasing as your speed is increasing. So since this force keeps on increasing with your speed, you see that the net downward force will start to decrease. Alright, because of which your acceleration would start to decrease. There will come a point when the viscous force would be equal to the gravitational force or net force causing the acceleration. Alright, which is gravitational minus the buoyant force. Alright. So finally, when such a situation is achieved, then the object will start moving with a constant velocity, which is called the terminal velocity. You can see the graph of V versus T here. Alright, this is the V versus T graph. This is how it would look, and eventually at infinite time, it would acquire a terminal velocity. Alright, so any spherical object of radius r and density rho is falling in a liquid of density sigma. Then the terminal velocity is given as this. This is the equation. This is very simple. What you do is you equate the viscous force equal to the net force causing the downward acceleration. The net force causing the downward acceleration would be mg minus buoyant force. Alright, so this is the expression that you will get. Now this you need to remember because a lot of questions are asked from this Stokes law and terminal velocity. So need to remember this. Alright, so let me maybe highlight this. You will need to remember this. This is something that you need to remember. So let me just write it also. Needs to be remembered. This is one expression that you need to remember. Alright. Okay, now let's move forward. Why don't we start with a practice problem? So this problem tells you that a plate of area of 2 meters square is made to move horizontally with a speed of 2 meters per second by applying a horizontal tangential force over the free surface of the liquid. Okay. If the depth of the liquid is 1 meter, the coefficient of viscosity of the liquid is 0.01 poise. Alright, then find the tangential force needed to move the plate. Alright, so try this problem. Alright. So why don't you try this problem? Let's wait for tomorrow discussion. What tomorrow discussion, Hitesh? What do you mean tomorrow discussion? Alright, by the way, for those of you who don't know, I today conducted a special class where I was talking about some of the biggest misconceptions about Newton's laws that people have. And this is what you are either studying wrong or understanding wrong. Okay, so I think that's a video where all of you guys need to watch. Okay. 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 So P Hitesh, you need to stop worrying so much about whether the exams will get postponed or not. And you just need to focus on studying and do not waste your time wondering whether whether the exams will get postponed or not. All right. I think you spend too much time worrying about that. All right. I think it's all right to keep yourself updated, but I think you should spend most of your time in preparing. All right. So Moisha is trying. How about others? I hope others are trying. It doesn't matter if it gets delayed. Then well and good. All right. Then all the more reason not to worry about this so much. Then also not to worry about it. You just focus on your studies. All right. Don't worry about these things so much. Your focus should be your studies, your time. You cannot waste your time. Doesn't matter if the JEE happens early or late. You should be utilizing your time and not wasting it. Worrying about all this. All right. Okay. So let's see. Yes, yes, yes. I know. But even then, you don't have much time to waste, right? Even then, you don't have much time to waste, do you? See, listen to Moisha. Listen to Moisha. That is a very great, good session. Actually, when your J exam is very near, then you will suddenly start feeling all the pressure. And then you will think, okay, at that time I was so involved in all this. Why was I not studying? I wish I had studied more rather than focusing on these discussions. All right. Now, all right. Let's see. Do we have an answer, Moisha? Do we have an answer from you? And I wonder where is Vineet today? No output. Okay. Okay. So this is very simple. You've been told. Okay. So let's go over this problem. So you have a plate here and you have some liquid. This is the ground. Now the fact that you use here is that the liquid layer which is in contact with the plate would move with the speed of the plate, and the liquid layer which is in contact with the bottom surface would move with the speed of bottom surface. Please remember this. Alright, please always remember this. So let's assume that there was a liquid here. Now let's see what all has been told to you. Hi Chinmay. What all has been told to you? So the plate of area 2 meter square. So the plate has an area of 2 meters square. So area is equal to 2 meters square. Yes, that is why I tell you should always make your diagrams. You should always make your diagrams. You should always make your diagrams. They will help you visualize the problem. I honestly can't solve any problem without making a diagram. It is very difficult for me. Okay, now you have been told that this is being moved horizontally with a speed of 2 meters per second. So this is being dragged on the side, okay, with 2 meters per second. Alright. And you have also been told that this length is 1 meter. Okay, Shyash Chaudhary says, sir, this is for which class? Okay, so this is essentially a quick revision, Shyash, for guys who have completed their class 11th. Okay, this is a class 11th topic, but this class is meant for revision. This is mainly this series that I host daily at 9:15 is aimed to help 2020 aspirants. Guys will be taking their JEE next month. Okay. Now, next thing that you know is that the coefficient of viscosity is 0.01 poise. Now, here be careful. Be careful about this. That this is not the SI unit. The SI unit is decapoise. Alright. Please remember this. Where is it? Yeah. The SI unit of viscosity is decapoise. So, decapoise, 1 decapoise is 10 poise. Okay. So I hope you remember this. So the conversion, this is the CGS unit by the way. Poise is the CGS unit. The conversion to the SI unit is that 10 of these would make 1 SI. Okay. So when you're writing your coefficient of viscosity would be 0.001 SI units. Okay, please remember this. Okay. Alright, now all you need to do is simply apply the equation. Hello Chenmay, hello, how are you? So obviously to keep moving this with a constant velocity also you would need a force. Why? That force would balance the force that is being acted on this plate. So this plate would feel some force in this direction due to the viscosity of the liquid. So it is already feeling a force, viscous force. To balance this, to move this plate with a constant velocity, you will need an external force. Alright, this is what you have been asked for. This external force would be equal to the viscous force in magnitude. Okay, so that is how you will calculate this. F external would be equal to F viscous, and F viscous I know again would be minus of F viscous, and minus of F viscous becomes minus neta A dV over dy. Alright. So now let's start substituting the values. So F external would be neta, which is 10 to the power minus 3. So 10 to the power minus 3 into area being 2, and into dV by dt. So dV by dy, how do we calculate that? We realize the speed of fluid here is, okay, so let's see. The speed of fluid here all the fluid is moving with 2 meter per second. Why? Imagine the fluid that got stuck to the plate. If some fluid obviously will get stuck to the plate, it will end up moving with the speed of the plate. How about the fluid at the bottom? So it has V equals 0. So your delta V from here to here, what is delta V? Delta V is 2. And what is your delta Y? Delta Y is 1 meter. Alright, so please remember that is how you calculate delta V or dV over dy. Instead of dV over dy, what you do is you use delta V over delta Y, assuming that it is constant and the liquid is homogeneous. Okay, so this would become 2 minus 0 over 1. Alright, so the force required turns out is 4 into 10 to the power minus 3 newtons. That is it. This is the external force that would be required to keep the plate moving with a constant velocity. Okay. Hi Vineet. I was wondering where you were. Alright, so please remember this. Now let's try one more problem. So you've been told in this, with what terminal velocity would an air bubble of 0.8 mm in diameter rise if the liquid of viscosity 0.15, again now this is SI, so this is fine. This is fine. Alright, and specific gravity of 0.9. The density of air can be assumed to this. So in this case what will happen is that the terminal velocity would be upwards. So it is not necessary that the terminal velocity has to be downwards. In this case, the net force which is causing the acceleration would be buoyant force, which would be higher than your mg. So the bubble would start to rise and would eventually gain an upward terminal velocity. Okay, so please remember this. Alright, you need to remember this. Okay. Alright, Vineet is trying, Moisha is trying. It's always good to see that these guys always try all their problems that are given to them. Okay. So here you don't have a problem with the viscosity because it is in SI unit in any case. Okay. All right, let's see some answers. All right. Okay. By the way, as I was saying, I don't know if you guys attended the session that I held today at 6. Was it at 6:30? Yeah, 6. So today I was talking about some of the biggest misconceptions that people have about Newton's laws. So you can attend that, and that may be very useful to you. All right, because there are a lot of wrong things that you think are correct. So that is definitely a video worth watching. All right, so that you get your concepts clear. All right, so Vineet got it. What is the answer, Vineet? What is the answer? 20. Okay. Now I honestly don't know the correct answer. I don't remember. I'll have to solve it right here. Okay. 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 So both of you are giving different answers. Okay. Let's see. That is interesting. So what all do we know about our bubble? So what all do we know about a bubble? The bubble has a diameter. So diameter has been told to me as 0.8 mm. So the radius would be 0.4 mm. All right. Next, what else do I know? I know the specific gravity of the liquid is zero point 0.9 and its viscosity is 0.15. So for liquid, let's see. For the liquid that we have here, the neta is 0.15 and density would be it was zero point 0.9 if I'm not wrong. So 900. Yeah. So I'm trying to keep all my units in SI. So this would be 900 kg per meter cube. And for the bubble, we have the radius as this, which would be 4 into 10 to the power of minus 4 meters. And similarly, the density of this, so density of bubble, what is that? The density of bubble is, the density of air, which would be 1.293. Okay, so it would be 1.293 kg per meter cube. Alright, now let's start solving. I know that when it attains an upward terminal velocity, let's say Vt, then what are the forces that you have acting on this? So you will have its own mg, you will have the buoyant force, F point, and then because in this case the buoyant force would be higher, so this would accelerate upwards, so the viscous force would act downwards. So please remember this. So you will have a viscous force which acts downwards. So you will have a downward acting viscous force. And at the terminal velocity, the bubble would be in equilibrium. No, Chinmay, I haven't planned any class for tomorrow. Maybe I'll plan something for day after tomorrow though. Okay, okay, Vineet. Let's see if you did that correctly or not. So for equilibrium, I know in when the bubble starts moving with terminal velocity, it will be in equilibrium. The net force would be zero because it is moving with a constant velocity. So now what I can say is that in this case, your Fv, the viscous force, must be equal to F buoyant minus mg. All right, let's start substituting the values. So this I have 6 pi neta r v, where Vt is the terminal velocity. This should be equal to buoyant force, which would be Vg, and I can say rho of liquid minus rho of bubble. That is what this side would become. Capital V being the volume, Alright, so this is how we get this equation. 6 pi eta r Vt equals, the volume is written as 4 by 3 pi r cube, alright, times G times rho minus rho bubble. So you get 3 here, you get 2 here, the pi get cancelled, 1 r gets cancelled, alright, and you will get your Vt as, again, you don't need to remember this equation. You don't really need to remember this equation. Trust me, I don't remember this equation. Alright, I just derive it whenever I need it. So its derivation, you see, is a one-line derivation. Okay, so it's not too difficult to derive. Alright, so I would advise you don't need to remember this. So this is what the terminal velocity equation is. Alright, I hope I derived it correct. Yes, it was 2 by 9 r square G over eta. Alright, so I seem to have derived it correctly. So that is what I was saying, that you can derive this very, very correctly. Now let's start substituting the values. So I will get 2 over 9 into r square. R square would be 16 into 10 to the power minus 8. Okay, into G, which is 10, over eta, which is 0.15. Again, this was given to me in SI, so I'm not bothering. Hi Lokesh, how are you? Alright, and again, now I have rho minus rho. So rho minus rho would be 900 minus 1. Okay, so yeah, these are some weird numbers. So let's quickly get this. So 900 minus 1.293. Okay, so that will be 898.707. So yes, the viscosity questions will have a lot of calculations. That is why IITs do not ask many questions, but mains people do, because they don't mind you solving so many equations or doing such heavy calculations. So let's try and find the value of this. So this is 2 over 9 into 16 into 898.707, and you divide this by 0.15. So what I am getting is okay. So the final answer that I am getting for terminal velocity is 2.13 into 10 to the power of minus, okay, 4 and 5 minus 3. That is the answer that I am getting. Okay, please check your calculations. You can check your calculations. This is the answer that I am getting. Alright, Lokesh, good to know. So please, Vineet, it won't be 20. It is 2.1 mm per second. Okay. It is this. I hope you guys followed the solution. Nope. Do your calculations. Maybe you did some mistake. Okay, or try and find a mistake if I made in my calculations. Don't just say no. Either find a mistake in my calculations or no, it's not 20. Then show me the correct calculations. Okay, I don't think I have made any calculation error. Yep, this seems fine, this seems fine, this seems fine. Yes, all this seems fine only. So you do need to check your calculations once. Let me just do the calculation one more time for your ease. It can't be 20. It can't be 20. You see, there is this 10 to the power minus 8 coming here. Yes, 0.8 is the diameter. You took that as radius. So that is what you need to be careful about. That is why I wrote r equals 0.4. The radius is 0.4. Please be very, very careful about the language. 0.8 was the diameter. Alright, you use radius in Stokes' law. Okay, so let me check the calculations again. So that's 2 into 16 into 898.707, okay, divided by 0.15, okay, divided by 9. Okay, so this is what I'm getting. So if I leave this here, I am getting this only. Vineet, you need to check your calculations again. No, 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 no. Of course I took it right. Of course I know. Okay, so this is 10 to the power minus 7. So what I am getting is all the other things are 21302.68 into 10 to the power minus 7. So obviously if you put it 0 here, this becomes 10 to the power minus 3. So you need to check your calculations one more time, Vineet, because this is the right answer. Okay. Alright. Please check your calculations, Vineet. It is not 20. It won't come out to be that big. Okay. Alright. Next, why don't we start our discussion about surface tension? Alright. So surface tension and capillary action. Alright. So what is surface tension? So surface tension can be defined as the property of liquid at rest by virtue of which its free surface starts behaving like a stretched membrane under tension, and it tries to occupy as small an area as possible. So experimentally we have seen a lot of stuff like you can balance a needle on the surface of a liquid when you carefully put it. Alright, a needle made of iron should not have floated. Alright. But it is a part of fluids. Yes. It is a part of fluids though. So I am covering it while covering fluids. Do you want it to be covered or not? Do you want it to be covered or not? It is still a part of fluids. I am covering it along with fluids. See, the topic today was viscosity and surface tension. It is still a part of fluids. How does it matter? If yes, in books it is given in different chapters. Who says I can't discuss it? Who says I can't discuss it with fluids? Okay, or in the same lecture. Okay. So experiments show that you can place a needle and it tends to stay on the surface of the any liquid. So that should not be possible. Why is that possible? Because the density of the needle is higher than density of the water. But you can still place your small pins and they will float on water. So what is causing that? So we realize experiments show that the free surface or the surface which is open to air, that is what a free surface is. Free surface is the surface which is open to air. That behaves like stretched membrane. Alright, as if you had placed a stretched membrane over it. Alright, if you place something here on the surface and if you look at it microscopically, with the help of a microscope, it appears as if the surface bends like this. Just like it would have happened on a stretched membrane. If you place something on a stretched membrane, then there would be some dip there, and the tangential components of the tension of the membrane would be balancing the weight. And that is what seems to be happening here. And this we are calling surface tension. So mathematically, surface tension is measured as the force experienced per unit length on any surface that is in contact with the liquid surface. So mathematically we are measuring it like force per unit length. Alright. So you see, if this is some length and if the net force across this length was L, then the force of surface tension would be measured as F over L. Not really, but the concept, it is just a concept. There is actually no real proof of this. We believe in it because it seems to explain every observation that we have made, and the formulae seem to predict the results so far. Alright, so it is a concept actually. The surface tension is an idea. We believe it to be true. Alright. And we have our own explanations for this. Alright. Now please note that the force of surface tension always acts perpendicular to the contact surface. So if you have this, so at every point the force would be acting perpendicular only on this side also and on this side also. So surface tension always tries to pull. So two things you need to remember this. The surface tension always tries to pull and it will always apply perpendicular to the length. Alright. So please remember these 2 points. Always applies a perpendicular pull force. Surface tension is always a perpendicular pull force. Okay. Next, let's move forward. So another observation, another experimental observation will show that to increase the surface area of liquid, work needs to be done. Hi sir, this is the first time I'm attending your class. Alright, most welcome to you, Anirudh. How are you? What class are you in? So what class are you in, Anirudh? Alright. So as I was saying, experimentally we can also notice that till the time Anirudh replies, okay, so class 12. So definitely you are at the right place. This will help you revise your class 11 topics. Along with that, if you want to study class 12 topics also, you can follow me on Tuesdays, Thursdays and Saturdays. There I am taking up class 12 topics one by one. Okay. Alright, so let's move forward with the discussion. So I was saying experiments also show that to increase the surface area of any liquid, work needs to be done. And hence some energy is transferred to the surface of the liquid. This additional energy is called the surface energy. So let me tell you what is happening. What is happening is that every molecule which is well inside the surface is feeling forces from all the directions. Alright, so it has no net force acting. However, what happens to the surface molecules? The molecules on the surface have an unbalanced force acting on them. The net force on them is downwards. Alright. No. No, I haven't. I will be starting with current electricity there. Magnetism I haven't even started. How will it be over? Now what happens is that when you are trying to pull this up, when you are trying to pull this up to the surface, when it starts coming closer to the surface, the net force acting on it is downward due to all the surrounding molecules here. Alright, so you have to do work against that attractive force to bring it on the surface. And we say that that surface, that energy, when you did work, you gave it energy. Where is that energy going? So we say that that energy goes into this interaction energy of all the molecules on the surface. So all the molecules on the surface, what they are doing is, you can imagine this. So all the molecules on the surface are holding each other, they are pulling each other strongly so that all the other molecules which are pulling these molecules downward cannot pull them down. So this interaction of all the surface molecules carries that extra energy that you have given it while doing work in pulling it from the some depth to the top. Okay. So that is what surface energy is. All the molecules on the surface have a certain energy due to interaction amongst themselves. Okay. When will current start? Okay, Vineet, I'll be starting current, I think, this week only. Okay, current electricity, I'll be starting this week. Don't worry. Alright. Now turns out that mathematically, surface tension can also be defined as the surface energy per unit area. Alright. So mathematically, I can define now surface tension in two ways. So surface tension is force per unit length, also it is the surface energy. So energy per unit area also. Alright, both these terms are always identical. Okay, you can experimentally prove this, but I am not going to show you because this is a revision class. Okay, so now surface tension, the magnitude of surface tension depends on the following quantities. One, the nature of the liquid. So for one liquid, the surface tension will have one value. For another liquid, it will have another value. Okay, L was the length on which it was acting. So let's see here. Let's see here. Imagine this has a length L, and on one side it is feeling a net force F. The net force that this rod feels on one side is F. Alright. Then surface tension is defined as F over L. Force per unit length of this. Okay. I hope you got that. Is that clear, Moesha? L is the length of the thing in contact. Suppose if I put this pen on the surface of water and let's say this side feels a force F, then L is the length of this. Alright, if the entire length is feeling F force, then surface tension is nothing but force per unit length of this. Okay, I hope that is clear. Sir, if we had a free surface irregular, then what will be L? Then small dl and df. Then small dl and df. See, even if you had a surface like this, then you can take any small portion. This would feel a force of df, and this has a length of dl. Then T would be equal to df over dl. Alright, I hope that answers your query. Okay. Wouldn't it be the line joining end point? Uh, I'm not sure what you're saying. No, 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 no. Never. No. Who told you that? See, you're talking about projections. You're talking about projections. What you are saying is then you need to find the net force in this direction. The force in every element would be in different direction. The force on this element would be in this direction. The force on this element would be in this direction. So if you found the net force, then that would correspond to the projected length. Alright. I hope you got what I'm saying. If you found the net force, that would correspond to the projected length. Okay. Yes. Yes. So that is something different. By definition, it is force per unit length. Alright. That result would come out to be true if again all the variables are uniform. Okay. So again, as I was saying, that the magnitude of surface tension, how can we find the net force? You can integrate that. Integral df. That is it. How else? Okay. The net force in any case would be zero, by the way. The net force would always be zero. Why? Even if you had a segment like this, the force on this side would be here, the force on this side would be here, the net force would be zero if you had liquid on both the sides. Yes, yes, you can do that while integration. While integration, what you are saying is if you had a soap layer, suppose if I had this, if I had such a segment and there was a soap layer here. Alright. Now because all the DFs on all the small DLs would be identical, so you can see that diametrically opposite, only these components would prevail. The perpendicular components would cancel each other out. Only these components would prevail. These components cancel each other out. So in this case, the net force is obviously this length. This length into T, that would be the net F. Alright, so you are right. You can use that. You can use that as long as, again, as I said, the surface tension has to be uniform. If I told you that there were some impurities in this area, then you can't apply that. If there were some impurities in some parts, then the surface tension would have different value, then you can't apply that. Then in the parts of the impurities, the surface tension would be df over dl here, would be T dash. Okay, I hope you got what I'm saying. Did you get what I'm saying? You can only apply the projected lengths if the surface tension is constant throughout. Because then what you're doing is, see what you're doing is, you're doing df equals t times dl. Now when you integrate this, when you're integrating this, there is the catch. You will say that integral of dfx would be t times integral dx, integral of dfy would be t times integral dy, and so on. Okay, that is why you're getting the projected length. But for that, the t has to be out of the integration. The t has to be out of the integration, which means the t everywhere should be the same. Alright. So that is where you can apply projected lengths. This is nothing projected x length. This is projected x length. This is projected y length. Alright. I hope that is clear now. The definition is t equals df over dl. Alright, the projected lengths are a result, mathematical result. Okay. Alright, so let's move forward. So as I was saying, the value of surface tension, by the way, is determined experimentally. It is determined experimentally, and the value of surface tension depends on the following: one, the nature of the liquid; second, the temperature; and third, the impurities. Alright, so you need to remember this. So why was surface tension acting in the first place? Why was surface tension acting? The surface tension was acting due to the interaction of these surface molecules, right? Surface tension was arising due to interaction of these surface molecules. So the interaction would depend, one, on the nature of the liquid; second, the temperature. Why? If you increase the temperature, things expand. So the average distances between these molecules would increase, and hence the interaction force would decrease. That is why surface tension decreases when you increase temperature. Alright, please remember this. Surface tension decreases when you increase temperature. Why? Because the average separation between the molecules increases, leading to a smaller interaction force between two surface molecules. Similarly, now impurities, in case of impurities, it may go either ways. Alright. Hi Balaji, how are you? In case of impurities, it may go either ways. Some impurities may act as bonding substances and may attract both, and hence increase the interaction between them. Some impurities might hinder it. So on adding impurities, the surface tension may also go up. Usually it goes down, but sometimes it may also go up. Okay. Next, so what are the mathematical applications? What are the questions based on in your JEE exam? So one very common category of questions is to find the excess pressure due to surface tension. So what happens is that if you have a drop here, if you draw the FBD of one half of the drop, so what is happening here? You will feel P external. So P external is applying the force. The surface tension is also applying a force in this direction. So this P inside has to balance the force of both, because of which inside a liquid the pressure is always higher than the external pressure. Alright, so this is what we call excess pressure. Excess pressure is P inside minus P external. Alright, and this is equal to 4R by T, 4T by R for case of a soap bubble. Why? Soap bubbles have two layers. Alright, two free surfaces. So every free surface is applying surface tension, by the way. So when you cut this soap bubble, you will see that it has two free surfaces. Okay, so there is liquid in the middle. It has an inner radius and it has an outer radius. And both these are open to air. The outer surface and the inner surface are both open to air. Alright, so this is what a bubble is, right? Okay, so it has a certain thickness. So it has two free surfaces. Both these free surfaces apply surface tension, and that is why you get the equation as delta P equals 4T over R. In case of a drop, okay, so if you had an air drop inside a liquid, so if you had a liquid and inside you had an air bubble, okay, so I think this has been, this is incorrect. This is the opposite. This is the opposite. So this should be 2 here and this should be 4 here. Alright, this is correct. So inside a soap bubble, so this is what bubble is. It has two free surfaces, that is why it's getting double the surface tension force. And this is a drop. In drop, there is only one free surface, okay? And for only one free surface, the excess pressure is 2T over R, okay? So please remember this. Okay or no? What am I saying? Oh, yes, 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 this was correct. Oh, this was correct. This was correct. Soap bubble it should be, soap bubble. Inside a soap bubble, it would be fine. And inside a drop, there would be only one free surface. Inside this kind of bubble, there will be only one free surface. Okay, this is an air bubble. So that is why I was getting confused. This can be an air bubble. So this will have only one free surface. So for this, you apply this formula. You do not apply this formula for this. And this is the drop. The drop also has only one free surface. So again, you apply this formula for a drop. So as far as you have one free surface, you apply 2T over R. If you have two free surfaces, then you apply 4T over R. Okay, so just remember that. Yeah, just remember that. Alright. So why don't we try a problem? So this problem says how much work is required to increase the diameter of a soap bubble from 2 centimeter to 5 centimeter. Alright, you've been told that the surface tension of soap solution is 3 into 10 to the power minus 2 Newton per meter. So this is the SI unit of surface tension, by the way, Newton per meter. So why don't you try this problem? Try this problem. Alright. Please let me know if you're trying this problem by writing trying in the chat. Okay. How about Vineet? Where has Vineet disappeared? Okay. Alright, so Moesha is trying. I hope others are trying as well. This is a fairly simple, straightforward problem. You need to know that surface tension was surface energy per unit area. So you need to find the increase in area, that would be, and that is where you can find the increase in surface energy, that would be the amount of work required. Okay. So my point is, whenever you're creating a free surface, you have to do work. Alright. And that work gets stored in form of the surface energy. Alright. Okay, let's see some answers coming. Come on. This is not that difficult. Shouldn't be taking this much time. Okay. Alright, hurry up, hurry up. Let's try this problem and give me the answer quickly. Okay, so Moisha says it is 791.6 into 10 to the power minus 6 what? Joules. SI unit, right? I hope. Alright, so this is nothing. This is very, very simple. The bubble was initially of some radius, then finally it has another radius. So initially it was like this. Alright, and so it had a radius of 2 centimeters. Finally, I expanded this to a radius of 5 centimeters. So finally, it became like this. Alright, only one thing that you need to remember, Moesha. that this is a soap bubble. I hope you took that into account. This is a soap bubble, so this will have two free surfaces. Two free surfaces, one the inside surface, another the outside surface. Alright. So the area that you will see would be twice the surface area. Alright. So please remember that. So if the free surface area initially was, so let free surface area, you have to take the free surface area. Free surface area initially is A1, and finally is A2. Work required is nothing but T into A2 minus A1. Alright, because T was the energy per unit area, and here you have to find the change in area. Yes, that is why I gave this problem. You need to be careful about that. In case of soap bubbles, there are two free surfaces, so both their areas are getting increased. Okay. So work required would be surface tension, which is 3 into 10 to the power minus 2, into the surface areas would be 2 times. So 2 times 4 pi r1 minus r2 square. So that would be point, again 5 square minus 2 square over 100 square over 100 square. Alright, so you need to be careful about all that. That is why I chose this question. I know you guys make those mistakes. So then this would be what? Okay, 6, 24, 24 pi into you have this is 25, 25 minus 4, so 21 into 10 to the power of 4 from here minus 6. Okay, joules. So let's just quickly find out the correct answer. Okay, so let's see. What do we have? 24 into 21 into pi. So I am getting my answer as 1.58 into 10 to the power of minus 3 joules. Alright. So yes, Moisha, you gave me half of that answer. That is why I gave this problem, because I knew you would make that mistake. So now please remember to read your questions very, very carefully. In case of soap bubbles, there are two free surfaces. Alright, so please remember when you're talking about the change in surface area, this 2 will be here. Alright. I hope you will remember this now. Moisha, is it clear? Please let me know. Okay. Anyhow, I think Moisha is feeling sad about the fact that that the 2 got missed. Anyhow, let's move on to the next problem. The next problem is yes. Okay. So remember that. So another practice problem. So what should be the pressure inside a small air bubble of radius 0.1 radius just below water surface if the surface tension is this? Okay, and atmospheric pressure is this. So please find this. So you'll find the pressure inside a small air bubble just below the water surface. Again, why am I using the term small? So that you can ignore the variation of pressure inside the liquid. Okay, if it was a large bubble, then it would change its shape because the pressure would be higher at the bottom area. Alright. Yes, air bubble it is. So air bubble, which means this has only one free surface. So now you will remember this. Soap bubbles have two free surfaces. Air bubble has only one free surface. Okay, one free surface only. So please remember that. Which equation do you use? 2T over R. Okay, and not 4T over R. Okay, so now you should be fine, I think. So just remember to read your questions very, very carefully. Where it is saying soap bubble, where it is saying air bubble. So please remember, air bubbles have one free surfaces and soap bubbles have two free surfaces. Okay, that is why I was correcting this here. That here it can't be air bubble, it has to be soap bubble. All right. So let's find the answer for this quick. Okay, so please write trying in the chat to let me know that you're trying this problem. Please write trying in the chat. All right, Vineet is back. Finally, I can see him back. So did you check that problem where you claimed that 20 meter per second would be the answer? I'm sure you had some data different. I have a feeling you ran off to check the answer of that. Okay, so Moisha says, okay, 1.014 into 10 to the power 5. Okay, let's see. That may be just correct. You know delta P. You know your delta P should be equal to 2T over R, which in this case would be 2 into 10 to the power of, okay, so 2 into 7.2 into 10 to the power of minus 2 over R is 0.1 mm. So R is 10 to the power of minus 4. So yes, this should be simple. This is 14.8. This is 14.8 into 10 to the power of 2 Pascal. And atmospheric pressure. Yes, I figured. I figured you probably don't have faith in me. And that is why you went looking for the paper. Okay, maybe I think sir is saying something wrong. Don't worry. PATM is, you guys should know, 1000 into 10 to the power 2 pascals. So P inside bubble would be this plus this. So yes, 1014.8 into 10 to the power 2 pascals. Or as Moisha correctly said, 1.0148 into 10 to the power of 5 pascals. Alright. So that is great. So let's try another problem. Okay. So a small air bubble of radius r is at a depth h below the water surface. The density of water is d and the surface tension is T and the atmospheric pressure is P. Now what is the pressure of inside the liquid? Yes, that is correct, Vineet. So no, he might be surprised if he had marked the answer wrong. Okay, maybe. Anyway, so let's try this one more problem. Again, you will realize every time you are being told small bubbles. Why? Again, so that you can ignore the variation of pressure due to liquid in the dimensions of the bubble. Okay, that is why you are always being told that these are small bubbles. If the bubble is too big, what will happen is that it won't even remain spherical. Okay, because higher pressure of the liquid below would cause its shape to get distorted. Okay, what is that? Okay, aha. Fine, why don't we try this problem then? This is very, very simple, very, very straightforward. So give me an answer quick. This should be very, very, very straightforward. Okay, still waiting. Still waiting for an answer, guys. P plus rho gh plus 2t over r, of course. Of course. Of course, that is it. That is it. That is absolutely correct. It is very, very simple. P would be P bubble. P inside bubble would be, let's just write PB. P inside bubble would be P plus rho gh plus 2t over small r. That is absolutely correct. No problem with that. Yes, absolutely. Very, very easy. Alright. So let's try one more problem. So this problem says that assume that a drop of liquid evaporates by decrease in its surface energy. Okay, so when it is evaporating, you can assume that its surface energy is consuming energy from the surface, and that is how it is evaporating. Yes. So that its temperature remains the same. Okay, so what is the minimum radius of the drop for this to be possible? The surface tension is T, the density of the liquid is D, and the latent heat of the liquid is L. Okay, so assume that a drop of liquid evaporates by decrease in its surface energy. Alright, so you have to tell me it's such that it has been said such that its temperature remains constant, by the way. Alright. Okay. Let's see, let's see. This is very, very important, very, very easy, by the way. This is not that tough. This is not that tough. Okay. You got two equations. Okay. I don't know. So this is, by the way, the latent heat of vaporization. I hope you guys know about this. This I'm talking about the latent heat of vaporization. This is the latent heat of vaporization. Okay. Yes, absolutely. That is how you will do it. Absolutely. Mm, 2T by PL. What is P? What is P? So yeah, this is very, very straightforward. The amount of heat required to vaporize would be small m times L, and this should come from the surface energy. Alright, the free surface. should get converted again is getting converted into gaseous state. All right. Okay. So what is the surface energy? Surface energy that you have. So I am saying the if the temperature does not change, so all the surface energy is only going into vaporization. All right. Surface energy is T times area. So you all you need to do is equate these since temperature doesn't change. So all this surface energy in evaporation would be going into the latent heat only. So since temperature does not change, what you can do is you can equate these two. So T into A must be equal to M times L. Now it's very easy. T into 4 pi r square should be equal to M, which would be 4 by 3 pi r cube times rho times L. Okay, so 4 pi r square, 4 pi and 1 r goes disappears. Okay, so you guys are giving some wrong answers. No, not 2t. It would be 3. So r would be 3t over rho L. That would be the answer. All right. This would be the answer. This drop can completely vaporize. Okay. This would be the answer. When I'm saying that it is vaporizing completely, what has been asked? Oh, are you okay? Are you saying the part of it is vaporizing? I'm talking about complete vaporization, by the way. I am talking about the complete vaporization. If you're talking about the part of it vaporizing, then probably what you're saying is correct. Then what you're saying is maybe correct. Okay, let's see what you. Okay, I get it. I was talking about the complete vaporization. If it gets completely vaporized. Okay. Otherwise, yes, you are right. dA would be 8 pi r dr, and dm would be rho dv, and dv would be 4 by 3 pi r square into 3 into dr. Alright, so I get it. I get what you're saying. Yes, then it would come to this. You are absolutely right. If you're talking about a partial vaporization, then yes. Then yes. What I meant was total vaporization. Okay, so for partial vaporization, this will be the case. Okay, all right, I get it. So it has not been mentioned clearly that whether the part of liquid is getting vaporized or is it getting vaporized completely. Okay, so that is where the confusion is, I think. Okay, not a problem, not a problem. In both these cases, you can have these answers. Okay, all right, all right. So this is for partial vaporization. The above answer that you gave 2T. Okay, the 2T one would be for partial vaporization, and for complete vaporization, you would have this. Okay. Anyhow, so we also talked about the fact earlier that the force of surface tension can also be calculated this, like this. So by the projected area, by the way. So suppose if you have this, if you have a quarter circle of radius r, so what would be the net forces on this? So just let me just tell you about this also. So what would be the net force on my quarter circle? What would be the net force on my quarter circle? The quarter circle would feel two forces, by the way. The point is that this is what Moisha was talking about earlier, that if you have any force acting on any small part, what you do is, let me show you the trick. So if you have a small part here and this has a force dF, now this dF can be divided into two components. Alright. So dF can have two components. So one is cos and one is sine. So you can say that dFy would be okay, so dF cos theta, and similarly dFx would be dF sin theta. And now what you do is you substitute dF as TdL, so TdL cos theta, and this can be substituted as TdL sin theta. Now when you're integrating this, when you take these outside, so Fy will be T times integral dl cos theta. dl cos theta, this is nothing but the projected length. So I just wanted to talk about this also very quickly. So what is dl cos theta? So if dl was this length, imagine if dl was this length, then dl cos theta would be this length. Alright, so this is dl cos theta and this would be dl sin theta. So what you can do is, when you need to calculate the net force in this direction, you take the projected length in this direction. So this is the projected length, and when you need to calculate the force in this direction, you take this projected length. Alright, that is how you can find both the forces. Okay, so this would be projected length. This is what projected lengths are. Alright, so you can remember this next. So T into this L. So Fx would be T into delta y, in fact, and this would be T into delta x. Alright, these are the projected lengths along the x and the y axes. Okay, so that is it. That is one more thing that I wanted to tell you today. Now let me wrap it up today. Tomorrow we'll be talking about capillary action. Okay, so I will discuss capillary action tomorrow. And day after tomorrow, I will start with thermodynamics. Alright, I hope that makes Moisha happy. Moisha had been requesting thermodynamics, and I realized that thermodynamics would make more sense. One, because that is a part of your chemistry syllabus also. So not only is it a class 11th topic, which is very important, it is also a part of chemistry, so it will help you twofolds. Okay. Yes, Moisha. Today I had 3 sessions, so I could not plan a longer session. Tomorrow I will finish surface tension, and then after that, when I'm talking about thermodynamics, I will plan that for thermodynamics. Don't worry. For thermodynamics sessions, I will try to wrap thermodynamics up in this week itself. All right. Don't worry. So this today's content was anyways smaller. I don't want to start capillary right now, because capillary would take more than half an hour. Okay, so that is the problem. Would take a lot of time. Capillary, all the discussion that I wanted to have, angle of contact, capillary, that alone would take 1.5 hours. All right. Don't worry. When I start thermodynamics, I will take your classes till 11:30. Okay, so don't worry. I will still finish the syllabus in time. Okay. I will finish thermodynamics I will try to finish that in 5 lectures, even if I have to take longer lectures. Okay, so don't worry about that. Let's just wrap it up for today. Let's come back tomorrow and start with capillary action. And I am feeling very tired and exhausted today, because I had 3 sessions today. Yeah, I know, but I am feeling a bit tired because I had 3 sessions today. So Just excuse me for today. Maybe tomorrow I can stretch. Okay, tomorrow I can stretch if you want. Okay, so that is it for today. You'll have to excuse me for one day. I don't want to stretch this session very much. Okay, so before I leave you, however, okay, I will try not taking too long. Okay, I will not take too long. Don't worry, don't worry. Okay, I will maybe stretch it by 15 minutes for 4 lectures. Okay, 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 no problem, no problem. All right, so before I leave you, let me remind you that you can get your Unacademy subscriptions by following these easy steps. Go to the plus section, select your goal as IIT JEE, and click on get subscription. All right. Now, when you're getting subscriptions, you will realize fees is very affordable already. You can make this fees even more affordable by using this code RDLive. Use this code, all right, in your Unacademy subscriptions and get an additional 10% off along with all the benefits that the Unacademy subscription comes with. All right. Now, if you like today's video, then press the like button and share it with your friends. Don't forget to press the bell icon to get notifications of all the lectures happening here, and the PDF of all the notes which were used in today's lecture would be available for download by, let's say, maximum day after tomorrow. All right. Don't forget to join us on the Telegram app using the link shown here. All right. Yes. Doubts, you will get your doubts answered today. Okay, Maisha, don't worry. Vineet, okay. Yeah, no problem, Moisha. All your doubts I will answer today. Don't worry. Vineet, in with the subscription, you will get even better quality, even more rigorous, more rigorous coaching. By the way, all right. There you will have DPPs, you will have detailed discussions, you will have more problem solving, and more rigorous analysis. Okay, don't worry. So definitely, trust me, the prices were also very small, and that price would be worth it. All right. Thank you. All right. So it's time for me to say goodbye to you for today. And before I leave, please let me remind you that you can get your Unacademy subscriptions with the RD code live code. All right. And this code will give you an additional 10% off. So I'll see you guys tomorrow again. All right. Bye bye and take care.